Not all bullets are the same. They don't have the same weight. Some have lead tips, others copper. Some have hollow points. Some bullets have lead cores. Others are made of harder metals. Bullet designs vary and bullet speeds are all different. In order to design a practical ballistic vest, you have to decide which bullets you're going to stop. Body armor has limits. Soft body armor designs are only effective for a specific range of bullet types and speeds. For example, a Type 3A armor is rated for a .44 Magnum with a bullet mass of 15 grams traveling at 1430 feet per second. As long as other bullets have similar characteristics, the armor will be effective. However, if you change the bullet type or the bullet speed, the armor may be penetrated. There are two types of body armor, hard armor and soft armor. Soft armor is textile-based and flexible. The yarns work to deform the bullet, and the layers deflect to slow the bullet to a stop, not unlike the way a net catches a ball. Hard armor is designed to stop bullets that don't deform, and is made of rigid molded plates or hard ceramic. Hard armor can't deflect like soft materials. It stops bullets as a result of strength and hardness. Most handgun bullets have lead cores and are deformable. Pistol bullets have limited speed because handgun barrels have limited length. For lead core bullets, soft armor is an effective solution. Rifle barrels are long and can generate high bullet speeds. Even lead-cored rifle bullets are moving too fast for most soft armor. Even worse, many rifle bullets have hard metal cores and are very hard to stop. As a result, soft armor is not very effective against rifle threats. Just to make matters a little more complex, we need to consider the threat posed by steel fragments or shrapnel from explosions. This type of ballistic projectile is of critical importance for military armor. However, more and more law enforcement programs are also concerned about IED and other explosive threats. Soft armor works well for IED and fragments, even though they are non-deformable steel projectiles. This threat type can be stopped by soft armor as long as the projectile weight is low and the speed is moderate. Military munitions and IEDs intended to attack personnel produce small projectiles moving at moderate speeds. Separate testing for performance against fragments is required in order to rate a vest for this threat. Soft body armor is made up of many layers of fiber that are laid up to form a ballistic panel. The key to soft armor is the yarn that is used in these layers. When a bullet strikes the armor, the yarn in the first few layers, known as the strike face, are loaded to the breaking point. The breaking force from the yarn is enough to cause the lead and copper to deform. As the bullet deforms, its energy is spread over more yarns, and it starts to distort the armor panel. The soft armor is now acting like a catcher's mitt. As the armor panel distorts, its back face is pushing into the soft tissue of the body. The panel and the soft tissue continues to move with the bullet until all the momentum of the bullet is gone. Some of this energy goes into the ballistic panel, and some of the energy goes into the body tissue. If the yarn is stronger, then fewer layers are needed to deform the bullet or fragment, and fewer layers of fiber are required to catch the round and transfer its momentum to the panel and body. Soft armor uses the strongest yarns and fiber made by man for this reason. There are many different ways to assemble yarn and fiber into a ballistic panel. There are wovens and there are felts. There are even non-woven laminates of yarn assembled with adhesive and film, like strapping tape made with fiber. Woven felts and laminates are used in various combinations in soft ballistic armor. In addition to the various ways to form ballistic sheet materials, there are a range of yarn types and sizes. For ballistics, there are two primary yarn types: the para-aramids, such as Twaron, Rusar, or Kevlar, and the ultra-high molecular weight polyethylenes, like Dyneema and Spectra. These fibers can be spun into very small yarns, such as those used in stockings, and they can be spun into very large yarns, like kite string. The smaller the yarn, the more layers in the vest. Because bombs produce small fragments, yarn size is important for these threats. If the yarns are too large or not packed together tightly, a small fragment can slip through soft armor. By comparison, bullets are large. Ballistic designers must consider a balanced approach to materials if both bullets and fragments are a threat. Every soft body armor design must define how many layers of fabric are enough to safely stop the projectiles required by the specification. The ballistic testing process provides data for the designer on the stopping power of a particular design and layer count. Wovens, felts, and laminates are affected by wear and use, so extra material must be included to ensure that vests continue to meet the required ballistic performance as the product ages. Because fabric materials wear, soft armor does not last forever. Each armor design should now include a warranted lifetime. Soft armor useful lifetime is usually between 3 and 8 years. Considerable work has been done to improve the testing methods for soft armor to simulate wear in order to measure lifetime performance. Keep track of the age of your armor and know your warranted lifetime. Know what threats your armor will stop. Be sure that your armor is rated for the ammunition and weapon you carry. Follow the care instructions provided by your armor manufacturer. What you know about your body armor could save your life.